everyone. We're going to see if we can, I started a little earlier trying to use a black screen here, and I'm going to just give up on that. We're going to just kind of go through, for those who are clever enough to go out and realize that hints are given all the time in this world. I'm going to talk about how one might go about using some mathematics, and turn that off here, to design. Really curious how Sal Khan gets that line tool to work, so I'm going to try my best here to design something like this. Something that's subject to a uniform load of W kips per foot. All right, is defined as, right, force over length. Very often kips per lineal inch, kips per lineal foot, pounds per lineal foot, etc. Span L is going to be typically inches, and deflection is going to be inches. And how one might go about designing something like this using mathematics to select the beam size so you limit the deflection to some number. So if we remember, we don't want to remember the individuals of all of these formulas. We do want to remember the two standards and some multipliers, and that is for a simply supported, uniformly loaded beam, right, subject to a load of W at a span of L. We know that this will deflect. See if I can do the color thing that Sal can do. We'll deflect down here. That didn't do it. Edit, undo, that did that. Let's see if we can do the color again. It will deflect, still not there, backwards, try it one more time. It will deflect, there you go, some distance there. However, a cantilever, instead of deflecting at a maximum, obviously at the middle, it will deflect, in effect, at the end at the maximum amount. So you're going to have this kind of concept there of deflection. So the formula, if you would, for the deflection of a simply loaded, simply supported, uniformly loaded, simply supported beam was that deflection max is equal to, remember, 5WL to the fourth power over 384 EI. And you remember that this one was going to be essentially almost 10 times as much, or 48/5 of that. Don't know why, we'll look at it later. And so the deflection max here is going to be equal to 48 times 384 WL to the fourth power over EI. And if in fact now, that's basically the equation, if now you want to solve for I, you can key in your delta max and you have something like I for this is going to be required I, or I SMOTA, is going to be 48 WL to the fourth power over 384 E times the deflection. Now if you notice here, oftentimes you might see that generally turning to a third power because you have very often the deflection given as a ratio of the span, but in this case maybe you know absolute numbers, and so let's go ahead and do that. Remembering everything must then be put in consistent units. So if we were doing a half an inch on a 10-foot beam, we'll do this, we'll do 1/2, let's not do 1/2 inch, let's do 1 inch on a 10-foot span, and eventually we're going to do it for a depth of, we'll try a 12-inch depth. So we can eventually talk about the section modulus and selecting the beam. So what do you have? Well, W has to be in kips per foot, kips per inch, and if we talked about here, we didn't really talk about it here, so we're going to tell you a little w is going to be 1,200 pounds per lineal foot, which is the same as 100 pounds per lineal inch, which is the same as 0.1 KLI, kips per lineal inch. And so we have then this formula solve out to be 48 times a W of 0.1 times a span. If we make our span 10 feet, that's 120 to the 4th power over 384. Remember, the modulus of elasticity of steel is 30,000 KSI, 29.9 times 10 to the 6th PSI, and the deflection that we said was 1/2 inch. So in that you have solve for the I SMOTA, and let's see what that looks like. That's going to be, and we're going to try to bring up again, not the best calculator, but a calculator, because it's pretty simple here. A calculator that says 48 times 0.1 is 4.8 times 120 times 120 times 120 times 120 equals, we get the top there, big number, however, divided by 384 divided by 30,000 and then divided by 0.5 divided by half doubles the number, and so we have a required section modulus of 1728. I'm sorry, I keep on saying that. 1728, let's see what that is. Again, 172, I'm sorry. So we're going to tell you that the required I SMOTA equals 172. Remember, that would be inches to the 4th power. And if we're going with a 12-inch deep, then the section modulus required would be that divided by 12, which would be 120, would be 10. So we're going to divide this by 12 and have to do it, longhand. So 12 goes into 17 one time, carry my 5, 52. 12 goes into there, 4, 48, and 4 twelfths. So we'll call it 48 and a third inches cubed. And now you are left then with, in fact, a required section modulus, and so you can go ahead and look for that section modulus in some table. So now we're back to the web or into Revit, and so what you do have is you want something that's a W10 shape, 10 by something. It's 100. That's giving you a section modulus 14, and I'm incorrect there once again. That looked a little low. You don't divide by the full depth, you divide by the half depth, so in fact you wanted here 28 as a section modulus, inches to the 3rd power. So that, of course, you can go out to the web, and we'll try to do that while we're still rolling as we would here, and see what the heck's there. There's the web. I'll bring down the browser so hopefully you can see it. We're just going to type in a very quick Google search here. Wide flanged beam section modulus. Let's see what it gives us. American wide flange beams. Well, there you go. From the engineering toolbox, kind of go through there and you look for eventually something. You're looking once again for the section modulus. And they're not actually, there it is, they do not actually give it there, do they? They don't give the section modulus, which is really, really a bummer. Oh, there it is, section modulus, static parameters. And so if you remember, you're looking for something in the order of 28. and we're looking at a W10, right? W12, I think, something in the order of 28. So something a little higher, the W12 by 26 will work. And what you then want to do is you want to make sure that you highlight and grab all of the information, including, the section modulus, the radius of gyration in both directions, this moment of inertia. And so this is not the best table, but in this case you can see you're going to design a W or select a W12 by 26, and that's going to help you then finally determine your stress as well, which we'll deal in a different video, or at least discuss about it. What you want to do is we won't put it in a different video, we'll put it here. So you have now, you're going to select a W12 by 26 with a section modulus of 33. So you're back to here, and you're going to just select, based on this, a W12 by 26, and the section modulus was 33. The last thing you want to know is the bending stress, which is equal to M over S. And then you have to now go back to another formula that we know, so we selected that. Another multiplier type formula, and I'm going to take advantage of this extra space up here to remember that for a beam, the maximum moment is simply supported uniformly loaded is WL squared over 8. But it was 4 times worse, or WL squared over 2, for a cantilever. You can go about that, doing that however well you choose. So it's going to be WL squared over 8 times 4. See, that one got a little screwy on me as I grab that, jumping around. All right, WL squared, you take that, multiply it by 4, knowing it's 4 times worse than on a cantilever than it is in a simply supported uniformly loaded beam. And so now you have, once again, your little W being 0.1 or 0.1 as the case may be. Length is 120. This time it's squared over essentially 2, and we have, that's going to be kip inches, and so we've got 120 squared. Back to the calculator. 120 times 120 times 0.1 equals, divided by 2, 720 kip inches. Boy, that number looks familiar. 720 kip inches, and you want to take M over S, so you're going to take the moment of 720 divided by 33, and you get 21.8. And so in this case you see 21.8. That deflection criteria just puts you to the point of being slightly over that 60% of the yield stress. So that turns out to be, selecting a W12 by 26 will get you that half-inch deflection. If that's, I'm sorry, we're looking at a 1-inch deflection here. I'm sorry, we did a half-inch deflection here. So that's going back to not the deflection, we used a half-inch. And you have to, of course, check for both criteria, that the bending stress is less than some required or allowable stress, with that really not exceeding 60% of the yield stress, and also that the deflection fits within some criteria. So you always check, try to do the color here. Okay, so check, not the color, try it again. Check for serviceability or deflection and stress. Jumped around a little bit, but what we want to remember is you want to get and learn the standard ones for simply supported uniformly loaded beam, and then learn the multipliers. Though you'll be able to reconnect, look things up, and do other like things, right? To do this algebraic solution. We'll turn that around, just checking the tools before I finish out. 0, turn it around. back to 0, so I can flip this thing around. Still looking for the line tool, but the great thing about one of these tablets is you can actually use a line. Thanks for listening.